Right, so let's start with what we did in grade 8. All right. So in grade 8, you were taught in grade 8, you were taught that if someone is standing on a planet or a moon or a star, not that you can stand on a star, you would be basically evaporated. But if you stood on a very, very big object, something that is, oh my word, something that is astronomically big. Okay, we're talking about something that's not like in our macroscopic world. We're talking about something like an Earth or a sun or a comet or a star, a moon, something like that. Then there's going to be a gravitational field, an invisible field around that object. And the result of that field is going to be, like with magnetism, where you have field lines along which objects will experience a force. I taught you in grade 8 that this invisible, this region in which gravitational force will be experienced is known as a gravitational field. Okay, so let's define gravitational field. All right, we're going back to what you previously have been exposed to. Gravitational field is a region of space in which a mass will experience a force due to gravity. Okay. Now, the older and the uglier I get, hopefully I get a little bit wiser, the more I realize how important language is in learning. All right, and unfortunately, the way we speak on a day-to-day basis can often work against our understanding the scientific concepts. So when we talk about gravity, we say gravity is a force. It's actually not true. Gravity is a phenomenon, not a force. Okay? It's actually been proven that gravity is actually not a force. Gravity is in actual fact the bending or the curvature of something called space-time. We perceive gravity by seeing objects being influenced by it. So we associate gravity as a force. But in actual fact, the force of gravity is weight. Gravity is a phenomenon. It's not a force. But associated with it is a force. Okay? If I can use an example. All right. A magnet, is a magnet a force? A magnet? No. Okay? Is the magnetic field a force? It's not. Does the magnetic field cause a force? Yes. If you put another magnet in its field, then you get a force, you see. So gravity is actually a phenomenon. We're not going to cleave hairs now, all right? We know that when you take an object, let's say we took an object like we learned in grade 8, and let's say we took Mr. D. Mr. D's mass is 80 kilograms after a bit of running and dieting. He's lost 5 kgs. Oh, yeah. All right. Okay, because I needed to, all drinking all those coffees. Okay. If my mass is 80 kilograms, that is the quantity of matter, a measure of the quantity of matter. Okay. So when we talk about an object that has a mass, that mass of 80 kilograms would be my mass irrespective of where my mass was measured in the universe at that instant. My mass is independent of gravitational field around me. But what happens is, by me being in the gravitational field of the Earth, I experience the force of the Earth on Mr. D. This is Mr. D. All right? Now, in grade 8, we gave that force a name. We called it weight. Remember that. So the force of the Earth on Mr. D, we called the weight, and we used a small w for weight, right? And we learned that the weight is the mass times the gravitational constant. Okay. Now, one of the beauties or beautiful things about physics is that it teaches you to look at things in a different way, as you're going to see. All right? So when you were in grade 8, I called that the gravitational constant. Do you remember that? 9,8 newtons per kilogram. So we called G, this was called the gravitational constant. And we said that it was dependent on the strength of the gravitational field. So in other words, the stronger the gravitational field, the higher the value of G. So for instance, G on the surface of the Earth is about 9,8 newtons per kilogram, but on the surface of the moon, it's about 1,66, 1,67, because the moon is smaller. Okay, so it's got less mass, it's got less, gravitational field is weaker. All right, so we learned that. We said, well, okay, weight equals the mass times gravity. Now, you will find in some textbooks, they also call this the force due to gravity. Have you seen that symbol, Fg? Okay, I think Mr. Himon in particular likes to use Fg. Does Dr. Rousseau use Fg? Also, Fg, okay? There's nothing wrong with it. It's totally acceptable. All right. If you go and you look at the matric NSC memoranda for the exams, you will see WFG, force of Earth on the object, doesn't matter. It's all accepted. Okay. We're cool with that. All right. Now, if we now go and we look here, I am going to add to this. This is the mass of the Earth. Right. The thing that causes the gravitational field is the Earth. So somehow or the other, this G here must have some form of dependency on the planet that is causing it. Okay? All right, I'm looking at this qualitatively now. We're going through it, just thinking of it on not in a mathematical way. Just think about it just qualitatively. So if I go and I look here, I say, okay, so G is dependent on the strength of the gravitational field. Of the gravitational field. This little squiggle here represents dependent. But now let's think about a planet. Okay, so we've got a planet, and let's say this is the mass of the Earth. Okay, and let's say we've got the moon, and this is the mass of the moon. Right? And we now are looking at the strength of the gravitational field. And we're saying, okay, well, G on the Earth, G of the gravitational strength of the field for the Earth is 9,8 newtons per kilogram. This is about 1,67 newtons per kilogram. My question to you is, why would it be that G here of the moon is less than G of the Earth? What do you see? Okay, so there's definitely a size difference, but there's also a mass difference. So we can say that this is dependent on the mass of the source
of the gravitational field.
So the strength of the gravitational field is dependent
on the mass of it. So the more mass, the stronger the gravitational field, the stronger the G value, or the bigger the G value. Okay? Right. Now, who of you know about black holes? You're right. Right. Black holes, the gravity is so strong that not even light can escape it. Okay. But how much mass is in a black hole? Have any of you seen this documentary, In Search of is it In Search of Infinity? What's it called now? No, not In Search of Infinity. There's another one, On the Edge of the Universe. It's about black holes.
Aren't black holes like weird because they crush you but they pull you at the same time and they twist you?
Yeah. Black holes is sort of the ultimate laboratory of physicists, because that's where gravity and quantum mechanics come together. Now, the thing I'm getting at is there's a huge amount of mass in a black hole. Okay? So in order for a black hole to be formed, the object that is collapsing when it's at its end of its life should be about 2.5 times or more the size of the sun. Any of you seen Oppenheimer, the movie? It's just come out. There's a thing in cosmology called the Tolman-Volkoff-Oppenheimer limit for neutron stars. Okay, and what it is about 2.4 solar masses. So if you have a star that's 2.4 times bigger than the sun, mass-wise, then it's going to be at its upper limit where everything inside is going to be collapsed into neutrons. It'll be a neutron star. But if you go bigger than that, then there's the pressure of the neutrons pushes against gravity, but gravity is too strong, and it collapses into a black hole. Okay, that limit, 2.5 times the mass of the sun and more, means that there's so much matter that the gravity overcomes any other repulsion. Why am I telling you this? Because then a black hole collapses into a very, very small region of space. Okay. So there's a reason why I'm telling you this. There is an inverse dependency on the size of the astronomical object. So what happens is, the smaller the physical dimension of the astronomical object, the bigger the gravitational force is going to be. Okay. So to give you an idea, there's a thing which is called the Schwarzschild radius, which basically is telling us if you took an object and you wanted to collapse it into a black hole, it would give you the radius of it. So let me give you, are you ready for this? If we took the Earth and we squashed it to the size into a black hole, it would be the diameter of a 5 Rand coin. If you took the mass of the Earth and you squashed it and squashed it and squashed it to the point where it became a black hole, the radius of that would be the radius of approximately a 5 Rand coin. Okay. The smaller you make the radius, the bigger the gravitational field. Because now your matter is causing gravity over a much smaller, more concentrated region of space. Okay. So we are going to see that in actual fact, the dependency here is 1 over the radius squared. So as the radius of a astronomical object decreases in the denominator, we find that the gravitational constant increases, right? And we are going to learn that G is proportional to the mass of the source over the radius squared. We are going to get to that next week, not now, okay? I am just starting with what you were exposed to in grade 8. And we are going to take that force of gravity, which we called Fg, or what we called weight, and we're going to take it and we're saying mass times G, but we're going to land up with the fact that this G is going to have a dependency on the mass of the source and an inverse dependency on the physical dimensions of the source. Okay. Now, it probably sounds like ancient Chinese in reverse at the moment. This is where we're going to get to. All right. We are going to use this next week. But now I'm going to approach it from a different approach. I am going to show you the first universal law of physics ever. Okay. Now, keep this in mind. We are going to come back to weight. Okay. Any questions at this stage? Okay. So just a little bit of background, linking it to what you did in grade 8 and grade 9. Callum.
Can you please show the first diagram that you showed? I just need to.
Sure. By the way, I'll post all of this. Okay. I'll post it. Okay. So, prior to Isaac Newton, there was a belief, and it had a religious influence, that because of the fact that we on earth were doomed and we were sinners, and the church told us how bad we were, that the laws that governed the world were different to the laws that governed the universe. They believed that up in the heavens were laws that were perfect, and on earth our laws were different. But Isaac Newton came along and formalized the first universal law. All right, and that law is this law. And I would like you to write it down. Newton's law of universal gravitation states that every particle in the universe exerts a force of gravitational attraction on every other particle in the universe. And this force is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Now, ladies and gentlemen, I haven't started off by just giving you the law. Because you can get the law and you can totally overlook the significance of this law. Isaac Newton spent his life trying to understand the physical world, trying to use mathematics to understand it, and trying to understand the spiritual world. Don't know how many of you are aware of this, but so Isaac Newton wrote as many works on theology, if not more, than on physics or mathematics. And he wrote a lot on physics and mathematics. He wrote Principia, which is like a set of books. All right. Isaac Newton was a deep thinker. And he saw things differently. So the mainstream belief was that the way those objects up in the night sky moved, were different to the way objects moved on the earth. Let me give you an example. If we take this and I drop it, that's what we see on earth. Okay? Isaac Newton looked at the moon, said, but the moon should fall as well. Does the moon fall? All the time.
Oh, okay.
It just falls past the earth. It's falling all the time. Okay? So if I stand on the top of a very, very high cliff and let's say I jump off of it. And let's say here's a high cliff. And I jump off of it. And then I run and I jump. And then I catapult. And then I put myself in a gun. Boom! And then I put myself in a hypothetical gun that shoots me at 5 kilometers per second. You'll miss the curvature of the Earth. And I keep on falling around it. We call it an orbit. The moon falls past the Earth. And what he realized is that the same laws that govern the way an apple falls on the Earth is exactly the same laws that govern the way a moon falls around the Earth. And what he realized is that everything in the universe was being attracted in the same way. Look at what it's saying here. It is saying that every particle in the universe is attracted to every other particle in the universe by the force of gravity. So what does that mean? It means that Imra, as she's sitting there, is attracted to Kishan. However, because Kishan is down on the field, the attraction is much less than what her attraction is to you. It's exactly what you're saying. Ladies and gentlemen, we think of gravity only acting down. It's not true. You and I are attracted to each other, but I'm attracted to the wall as well and to everything around me. That is a crazy thought, ladies and gentlemen. Do you know that they measure the mass of mountains by measuring the gravitational attraction of the mountain on certain instrumentation? Gravity doesn't only act down, ladies and gentlemen. It acts in all directions. If you had to dig a tunnel through the center of the Earth, and you had to go to the center of the Earth, you would be weightless. Because in the center of the Earth, every single particle in the Earth would pull you in the direction toward it, and so you would have a zero resultant force on you.
So how deep would you have to start digging so that your down becomes your new up?
You have to go to the center of the Earth. Okay. And so, ladies and gentlemen, this was beyond a revolutionary idea. It wasn't an anti-God idea at all. Isaac Newton was deeply religious, all right, to the point, to a fault. He was deeply, deeply religious. He wasn't trying to push an agenda here that God was wrong and the church was wrong and that. He basically worked out that the only way he could at that stage explain what was happening was to assume that it was happening also off the Earth. And so we now come to a revolutionary idea. And the idea is the following. Let's say we have two particles of matter. Let's call this particle mass 1, and let's call this particle mass 2, right? And we take these two particles, and let's say that these two particles are the bottle and the mug. And let's say I am going to put them 30 centimeters apart. For the benefit of the people who are seeing the recording, I'm going to put it 30 centimeters apart. Now, so we've got a mug and we've got a bottle. Let's say that the mug, there's the mug, excuse my drawing, okay. Let's say my mug has got a mass of 350 grams. I want you to do this with me, all right? This is the mug. And let's say that the bottle, okay, has a mass of 420 grams. Okay. And let's say we take our ruler and we put the distance between them such that the center of mass of the two objects is 30 centimeters apart. So the distance between these two is 30 centimeters. Newton said the following. He said every single particle in this bottle is going to be attracted to every single particle in that mug. And every single particle in that mug is going to be attracted to every single particle in that bottle. Okay. Now, just as I was about to tell you a story, Dr. Ronderbeck comes in. In my younger days, when I used to club, man, this is what you're looking for.
Yes, that is what I'm looking for.
Yeah, the only problem is it's made for midgets.
Very wonderful.
They're very simple. In my younger days, when I used to club, on a Friday, I used to go into the club and they used to check the girls out. Us guys, scanning the field. Go like, gee, dude, I'm attracted to that chick. The problem was, physically speaking, I was more attracted to my hairy mates than what I was to them. Because firstly, they were closer to me, and secondly, they had more mass than what she did. That's the scary part, is in actual fact, you're attracted to everything. All right. But your distance affects how much you're attracted. So fortunately, the further away you are, and I go, wait a minute now. Have you ever been attracted to the wall? Have you ever walked like this and go,
On a bad day, yes.
I'm not talking after I've had too much whiskey. I am talking about, have you ever felt, gee, I can feel the force of gravity against the wall? No, you haven't. There's a reason why. There's a very, very, very deep reason why. Because gravity is the weakest of all forces. But Sir, it shapes the universe. Yes. But it's also super weak. But the amazing thing about gravity, unlike electrostatic forces and magnetic forces, which are repulsive and attractive, gravity is purely attractive. So even if it's weak, if you keep on clumping matter together, guess what happens? It gets stronger and stronger and stronger attractively. Now, I'm going to prove to you that this is true. So let's go now and look at what Newton's law of universal gravitation says. It says that the force of attraction is directly proportional to the product of the masses. So what that means is, if I look at the force of gravity, let's call this Fg, and I take two particles, mass 1, and I multiply to mass 2, I get direct proportionality. What that means is, as these masses get bigger, what happens to the force of attraction? It gets bigger. But then he also said that the force, so this is that. But he also said that the force of gravity, if we take the force of gravity and we measure the distance away, the distance between them, you can use d or r, we find that it's inversely proportional. And so if you put the two of them together, you get this. And if you have a proportionality in mathematics, just take a look at this. If I say to you, in mathematics, if I've got y and x, and I have a proportionality, isn't this a graph y equals mx? Isn't this a graph y equals mx? Plus c, and c will be naught. But that m is a constant of proportionality. It's the gradient, eh? But ladies and gentlemen, the gradient of this versus this gives us one of the fundamental constants of the universe. It gives us the constant of universal gravitation. And it's tiny. And it's tiny because gravity is fundamentally weak. So if we look at this formula, this is the mathematical form of this. So please write this down. Okay? F equals G, but it's a big G. This is the universal gravitational constant. the universal gravitational constant. This is not little g. This is not little g. This is big G. This is a universal constant. This is something that is true throughout the universe. This is one of those constants, like one of the fundamental constants, like what is the charge on an electron? Negative 1,619 times 10 to the negative 19 coulombs. What is the charge on a proton? Plus 1,619 times 10 to the negative 19 coulombs. This is not something we can change. This is something we have measured. And it's a really cool story because the guy who measured it was an absolute weirdo. His name was Henry Cavendish. And Henry Cavendish was of nobility. He lived in a ginormous mansion. But he was such an introvert, he could not even speak to people who came to his parties. He would have his butler speak. He would speak to his butler, and his butler would speak to people. That's how introvert he was. But the guy was cool because you know what he did? He actually measured the strength of gravity by measuring a torsion balance with a telescope through a keyhole to see the reading in order to see how much one little metal ball was actually twisting this torsion balance through gravity. Oh yeah, he was a weirdo, but he gave us the strength of gravity in the universe. It's the reason why they've named the Cavendish laboratories after him, Henry Cavendish. Okay, so let's now go and take a look here. What is the value? Oh my word, that's small. Oh my word, that's tiny. That, ladies and gentlemen, is the gravitational constant for gravity in the universe. And we in NSC use 6,67 times 10 to the negative 11. 6,67 times 10 to the negative 11. All right, and if you're wondering where these units come from, I will show you. If you take F equals G, and you take M1 times M2 over the distance squared, and you multiply by D squared on both sides, and you divide by mass 1 and mass 2 on both sides, you get G. Now let's look at G. What are the units of G? Well, force is measured in newtons. Distance is meters, and we square it. And mass is kilograms, so that's kilogram times kilogram is kilogram squared. So this is Newton meters squared, kilograms to the minus 2. That's where the unit comes from. Now, this is tiny. 10 to the negative 11 is tiny. And that is why we don't experience gravity sideways. Because even though the two of you are attracted to each other, your masses are so small that, and when you multiply them together, 10 to the negative 11 times the product of your masses still is 10 to like the negative 9, which you don't experience. But the Earth is huge. So the Earth has got of the power of 10 to the 27, which when you multiply to this, starts to make it significant. It's 10 to 24, actually. Okay. So now, let's go and take a look at our example. So what we know is that ultimately, these two are going to attract each other. Have you done Newton's laws yet? You haven't done. So you're going to learn about Newton's first law, second law, and third law. Newton's third law basically says, for every action, there's an equal and opposite reaction. So if object A acts on object B with force F, then object B acts on object A with force F, but in the opposite direction. Same magnitude, opposite direction. It's called Newton's third law. Okay. Now, let's do this. F equals G mass 1, times mass 2 over the distance between them squared. So let's now go and put this in. So we say F equals, by the way, the constant for gravity gets given to you on your formula sheet. It is 6,67 times 10 to the negative 11. Do not worry about the units. You don't have to worry about the units. Your mass needs to be in kilograms. So this is going to be 0,42 kilograms because we divide by 1,000. There are 1,000 grams in the kilogram. This is going to be 0,35 kilograms. All right, we divide there by 1,000. So what we have here is we have mass 1 is 0,42 kilograms. Mass 2 is 0,35 kilograms. And the distance between them, we've got to go to meters. So we've got to divide by 100 in order to go from centimeters to meters. So sorry, that's going to be 0,3 meters. 0,3 meters squared. Now, if we work that out, let's work that out. Let's take our calculators and let's work that out. Six 6,67 times 10 to the negative 11 times 0.42 times 0.35 divided by 0.3 squared. We get that the force of gravity between them is tiny. Ladies and gentlemen, this is tiny. 10 to the negative 10 newtons. We can't feel that. Our bodies aren't sensitive enough to feel that. Okay? So, the force of gravity is in actual fact a weak force. The only time we actually physically see the effect of gravity is when one of your masses at least is really big. Okay, so if you take this formula here, if one of these masses is astronomical. Now, when I say astronomical, I'm not talking about a few thousand kilograms. I'm not even talking about a few million kilograms. I'm talking about quadrillions of kilograms, okay? I'm talking like 10 to the 9, 10 to the 12, 10 to the 15, 10 to the 20 kilograms. Right. I want you to do something with your cell phones. I want you to please find the mass of the Earth for me, please. The mass of the Earth. Just quickly on your cell phones. If we take the mass of the Earth.
Okay. That's a big number. Should we say it?
What is the mass of the Earth?
5.97
Times, times 10 to the?
24.
That's it. 10 to the 24
Kilograms.
Okay. Now, can you find out what the radius of the Earth for me is, please?
6,378.1 kilometers.
6,378 kilometers.
Yes.
Okay, and my mass is 80 kilograms. Okay, now let's do a different calculation. All right, so this was example 1, where we worked with non-astronomical objects. Non-astronomical objects. But now let's work with one astronomical object. I'm not an astronomical object, okay? So this is non-astronomical, but this is astronomical. So what I'm going to do, I'm going to take the center of gravity of the Earth, and I'm going to take the center of gravity of myself, and I'm going to basically say that the distance between my center and the center of the Earth is about the radius of the Earth. I mean, the 1 meter between my center of gravity and the surface compared to 6,500 kilometers, meaningless. So what should I do now? You're going to do it with me. This is example 2. This is example 2. So example 2, one of the objects is astronomical. This is non-astronomical. You only need one of them to be astronomical. Okay, so watch what we do. We say, okay, we know there's going to be a, wait a minute. Didn't Newton say that not only was the apple falling, but the earth was falling to the apple? Because they're both attracting each other. The earth falls up when something is falling. But because its mass is so big, the acceleration is so small. When you learn Newton's second law, acceleration is force over mass. If the mass is so big, your acceleration is virtually zero. There is one little problem. You guys haven't done Newton's laws yet. And normally when we do this after Newton's laws. It's okay. It's not the transformation. Okay. There's a reason why we're doing this, because we want to get to acids and bases next. Okay. So we're getting this done. All right. So let's work this out. So the force of gravity is G, mass 1, mass 2, over the distance squared. You use D or R for distance. It doesn't matter. The reason why you can use R for distance is because gravity is spherically symmetrical. You can actually find the same force on a surface of a sphere of radius R. Okay, we can use R or D. So let's go. So we go, okay, so F equals 6,67 times 10 to the negative 11. Mass 1 is 80 kilograms. Mass 2 is the mass of the Earth, is 5,97 times 10 to the 24 kilograms. I want to show you something. Do you see this power here? Dominates this power. As soon as this power gets bigger than that power, you start to feel gravity physically.
So should we divide once?
No, we are. We absolutely. Now we divide by the distance between, but now you've got to be careful. This is 6,378,1 kilometers, which is 100 meters. You've got times by 1,000. And so we square. So it's got to be that distance in kilometers must be in meters.
And the weight, shouldn't it be in?
The mass must be in kilograms. By the way, this is the weight. I'm going to prove to you this is the weight. So if we now go and we work this out, we go 6,67 times 10 to the negative 11 times Mr. D is 80 times 5,97 times 10 to the 24 divided by 6,378,100 squared. Oh my word, I get my weight. The force of the Earth on Mr. D is 783,082 newtons. The force of Mr. D on the Earth is also. But if I were to go and say weight equals mass of Mr. D times G, then what I get is, okay, this is 80 kilograms. G we know is approximately 9,8 newtons per kilogram. So therefore, what's 80 times 9,8? Hello, ladies and gentlemen. We have just generalized weight. We can now work out the force of gravity anywhere, even if we don't know what little g is. And that is cool, because now we have a universal method. This gives us the opportunity to now work out crazy stuff. So here's something crazy. Do you want to work out the force of the Earth pulling on the moon? I do. I do. Why don't we do it? Okay, are you ready? So let's go. So if we now go and we look at example 3, we are going to take the moon. There's the moon. Now we need 2 things about the moon, which we would normally give you. We need the mass of the moon. Can someone give me the mass of the moon, please? Thank you. Tamlin, you're so good at it. Just go and check quickly. And I want the radius of the moon, please. The radius of the moon. So what's the...
Okay, I'm going to round to 3 decimal.
Yeah, 3 decimal places.
7.348.
Times 10 to the 22 kilograms. Radius of the moon?
1,737.4 kilometers.
That's fine. Okay, then if we look at the Earth, there's the Earth. We've got the mass of the Earth. We said the mass of the Earth is 5,97. The mass of the Earth is 5,97 times 10 to the 24 kilograms. All right, we have that the radius of the Earth is 6378,1. 6378,1 kilometers. Okay. Can someone tell me what the distance is between the moon and the Earth? The average distance.
Is this 2 astronomical objects?
Okay, what is it?
No, I'm asking. Is it 2 astronomical objects?
2 astronomical objects. Absolutely. I mean, you can see here. Look at the powers. They're 2 astronomical objects. So now, example 3 is 2 astronomical objects.
So in a test, for example, can they make up, like, say, planet X, and then just give us a random?
We can give you all sorts of stuff. We're only doing the basics yet. We can give you the force and ask you what the mass of one of the astronomical objects is.
Yeah, so, but it can be like planet X. It doesn't have to
Oh, yeah. No. We'll give you strange stuff.
Oh, okay.
We could give you like a comet, for instance. There's, I mean, with science, you can always make, even the simplest thing, you can make it complicated by putting in context to it. All right, what's the distance between the moon and the Earth?
Did you get it?
No. What you were getting?
So they slow. What is it, Isabella? 384,400 kilometers. Just by the way, have any of you seen the Netflix movie now, the documentary? They brought out some amazing documentaries called Unknown Robot Killers. Have you seen that one? With AI and swarm theory and that with drones. That is scary. The one, have you seen the Unknown Time Machine? It's about the latest James Webb telescope. The James Webb telescope is 1,000,000 kilometers from the Earth. And they have just found stuff that they've never seen before. What they think is antimatter stars.
What is that?
Antimatter stars, what they call dark stars, where they are generating energy through antimatter annihilating. They thought they were dark galaxies, they are dark stars. The James Webb has seen stuff that we've never seen before. Yeah, crazy.
So is it like a star made of?
Just go and check, just go and look at dark matter the dark stars. They are millions of times the size of the sun, but they are thought to be made out of antimatter.
What is that?
It's the opposite of matter. So if you've got an electron, you have an electron, the anti-electron is a positron. And if I could just give you, sorry, now I am bragging a little bit, but this holiday, I was at CERN for 2 weeks. I was in the only place on Earth where they actually produce stable antimatter. I was in the antimatter factory at CERN.
What happens if it's unstable?
Well, it is unstable. It lasts for a few hours, and then they put it in a trap, and when it touches matter, it annihilates immediately.
I didn't know you could make it.
They've made anti-hydrogen. They make anti-hydrogen at CERN. If you read the book Angels and Demons, they talk about, or the movie where they steal the antimatter, it's from the antimatter factory at CERN. I'll even show you a photo. I'm standing there in front of the antimatter producer.
I follow you on Instagram.
You saw it.
How does antimatter look like? Can you see
You
it?
can't see it.
Is it too small?
It's too small.
Okay.
That,
All right.
sorry.
Okay, sorry, that was a bit of bragging, but I think that was
It's
antimatter.
fine, you deserve it.
Antimatter is pretty cool. Okay, so now, yes,
If you can see matter, right, using.
you can't see matter. Not on that scale. Can you see a hydrogen
Of course not
atom?
on that scale.
You're not going to see a hydrogen anti-atom either, anti-hydrogen.
A large amount of matter you can see with light, which is photons, right?
Yes,
Could you do the same
you
thing?
can. You would be able to see antimatter, but what you can't see is dark matter. They're different.
What's the difference?
Dark matter doesn't give off light. That's why it's dark. Okay, now, all right. Let's assume, wait a minute, let's assume that the distance they've given us is between the two surfaces. Okay, let's assume the distance they've given us between the two surfaces. So what you do now, ladies and gentlemen, is the following. There is a force of the moon on the earth and a force of the earth on the moon. Wait a minute, force of the moon on earth causes tides. That's why we have tides in the ocean, because the moon pulls on the surface of the earth and pulls on the oceans and creates tides. And as the earth spins, it goes through sections where it's facing the moon and sections where it's moving away from the moon, high tide and low tide. The fact that we have tides on earth is due to this. And the fact that the moon falls past the earth is due to this. Let's work out F. So F equals G, mass of the moon, times mass of the earth. Now this you need to be very well aware of. When we deal with this law, ladies and gentlemen, you actually need to be careful. Yeah, we should actually say the square of the distance between their centers. We need to refine this between their centers. When you're working with astronomical objects, their physical size is so big, you can't overlook their physical dimension. Okay, so what we do now is we work out the distance from this center to that center. Now, what is that distance? It's going to be 6,378,1 kilometers plus 384,400 kilometers between the surfaces, plus the radius of the moon, which is going to be 1,737,4 kilometers. So when we add all of that up, we get the distance between their centers, 6378.1 plus 384,400 plus 1,737,4. And what we get is 392,515,5 kilometers. But when we put it into here, these need to be in kilograms, and this needs to be in meters. And that's a common mistake. A common mistake when grade 11s do this is they don't work with the distance between the centers, and they don't work with the distance in meters. So now, when we do this, we say, okay, so F equals 6,67 times 10 to the negative 11. The mass of the moon is 7,348 times 10 to the 22 kilograms. The mass of the earth, we said, was 5,97, eh? 5,97 times 10 to the 24 kilograms over the distance squared. Now the distance is big, eh? The distance is big. It's 392,515,5 kilometers times 1,000 meters per kilometer. So you've got it to have it in meters, you actually got it times by 1,000. And the other mistake learners make is they forget to square the distance. So let's do that. So we work it out and we go, okay, 6,67 times 10 to the negative 11 equals times 7,348 times 10 to the 22 times 5,97 times 10 to the 24, okay, divided by 392,515,500 squared. And ladies and gentlemen, the force between the Earth and the Moon is significant. Wow. Did you think that when you walked in this afternoon, you would walk out having been able to calculate the force between astronomical objects in the universe? No. Thank you, Newton. And you know what, ladies and gentlemen? This is what the satellite engineers use. They work out what speed they need to get the satellites in orbit, because at a certain distance, the force, they work out the force which causes what they call the centripetal force, is the force of gravity. Now, okay, if you do AP physics, you do this stuff. All right. Do you know how far away the satellites are that we need in order to use GPS? What they call geostationary satellites. Have you got any idea how far away they are from the surface of the Earth?
Maybe 1,000 or more.
30,000.
That's quite a lot. But
They
that's
put your DSTV and your GPS satellites 30,000 kilometers above the Earth's surface. And it's got to spin at the same rotational speed as the Earth, so it remains stationary above that point on Earth. 30,000 kilometers above the Earth's surface. The International Space Station is only about 400 kilometers above the surface of the Earth.
That's a lot.
We are using this stuff, ladies and gentlemen, for satellites, for space stations. This stuff, what we're doing here.
So
Yeah.
does that mean that if they're not careful, they could pick up the International Space Station on like GPS, like on like
I think it's on a different frequency. They work on different frequencies.
No, but like if they were to take a photo or something.
Okay, so what we're starting to pick up is a big problem. It's called space junk.
Yeah, I was just
Okay,
about to mention
and let me
that.
tell you, Elon Musk is adding to it with his, is it Starlink? What's this
I
thing?
think so.
Yeah.
Okay. If you look carefully, some mornings you can see 6 satellites in a row.
Yes.
Yeah,
I've
it's
seen it
these
before.
green lights. It's also.
No,
the
it's
red
not
lights.
UFOs, it's satellites.
What? I've never
I've
seen
seen
it.
it
It's
before.
at camp. It's like these green lines. They go like
They go like
this around and they go
I've
like
never
this.
seen
It was
It's
at
crazy,
camp.
sir.
Can you
It's
see
cool.
it?
Okay,
I've never seen it
so
at
so
camp.
ladies and gentlemen, despite what the skit says, I never taught Elon Musk. It says I taught- All right, okay. So now we have these exercises that I would like you to do, all right? And if you're going to come to the workshop next week, then I would like you to have these done, and then we'll go through them quickly. But please do these using F equals G M1 M2 over distance squared. And that is it. That is the end of this workshop.
So of these activities in the notes.
These are in the notes. It sits on page 4. If you can do those for me, please. And if I can just ask, Dr. Rousseau wanted to just make sure that we have the people who were here. But I'm just going to ask you before you go, to just please write your name and surname on here. Thank you. And I will post my notes that I have made here I will post on Classroom. I'm going to stop the recording. All right, and I will post that too.
Just the normal classroom? Or is
The general one. The general one. Yeah, the general one.